machine learning, and that can be, maybe we've got some private inputs that we're giving to a machine learning model, and we don't want that to be made public. For example, if you're chatting to ChatGPT, maybe you don't want all of that information to be spread elsewhere. But also for the people who are creating these models, there's a lot of business value in the models themselves. Maybe they don't want all of that to be taken elsewhere. All right. So I need to give you a quick background into two aspects. First of all, zk, and then we'll do ML. So zero knowledge proofs. So they give us two sort of aspects. One is the fact of verifiable computation. You can do some computation and then prove that that was done correctly. The second aspect, and one I guess we'll be thinking about more, is the idea of privacy. It's the zero knowledge part of zero knowledge proofs. You can have some input to a computation, and you can get that proved that that computation worked correctly, gave the correct output, but without revealing what that input was. Okay. And there are different ways that this can work, different types of zero knowledge proving systems, snarks and starks, bulletproofs, lots of different protocols. This diagram represents kind of an overall process, but we don't have to go through that. If you want to know more about it, I could talk about it later. Machine learning. So, machine learning, what this usually consists of, particularly what I'm thinking about today, are neural networks. What these are made of are many, many layers. We go through these layers, we put an input in one side, we go through many layers, processing this input, and we get to an output layer. And each one of these layers has this kind of structure. So this is kind of representing a layer. We've got some inputs going in. We have these things called weights. So these are the actual data that the model holds. And this gives us a weight-adjusted value, which comes to the next node in the next layer. And then we have things called activation functions. This says, should this node actually send an output or not? Okay. So it's a quite simplified version, but that's roughly what machine learning neural networks look like. There's two parts to machine learning. There's a training part and what's called the inference part. With zkML, we're particularly interested in the inference part, or rather, we have to be interested in the inference part because of the performance of training. Makes it very difficult to do the zkML on the training part. The training part is where we actually get these weights set up. What you do is, for the training, you give it some inputs and you tell it what outputs you're expecting, and then we adjust the weights until we get the correct outputs, and that's training the model. And for large language models, such as ChatGPT, this can take a long time. This can take months of work. It can be very expensive, and the number of weights we end up with is in the trillions. Okay. Now, what would we do with zkML? What sort of general process could we be thinking of? Well, if you imagine you're a consumer of some kind of machine learning model, okay? You're sending off some input to a machine learning model. That model has certain weights set up, and the person running this model has told you that, yeah, this is absolutely the best, most expensive model they've got. You're going to get the best results from this. And they sent you the output of this model. But the point is, how do you know that they actually did that one? They didn't do a really cheap model and, maybe it doesn't work so well. Well, the point of zkML, at one point, is that you can get a proof of what model was actually used when the model ran. And then that can come back to you, and you can then verify it and say, yeah, okay, I got the output and I know how this was derived. All right, now, some of the challenges. So, zero knowledge proofs, they prove computation, any computation at all, okay? They create a proof of that. And machine learning is just some computation, so it should be easy to do zkML, surely. It's just another computation, so why not? But there is a big problem. The underlying mathematics behind zero-knowledge proofs and machine learning is vastly different. Zero-knowledge proofs rely on what are called finite fields. These are fields of, these are integers. There's a maximum value, which is a very restricted kind of mathematical environment. And zero-knowledge proofs work in that environment. Machine learning doesn't use that. It is much less restricted. It uses floating point arithmetic, it uses matrices. Getting these two things together mathematically is very difficult indeed. Okay. Also, there's a problem that these are quite complex areas. Machine learning is a complex area in itself. Even with these models, we can train them, but once we've trained them, they give an output. We don't always know exactly how they came up with that output. We don't exactly really understand them. Zero-knowledge proofs, similarly, we can use them, but they include very advanced cryptography. So getting the two together is, just doing the complexity squared. And what we need, one of the basic problems is trying to get that machine learning, this thing that has floating point numbers and all this floating point arithmetic, and getting that done with zero-knowledge proofs. Okay. The reason why we want to do this, privacy, what I'm talking about today, we want to be able to have private inputs to our machine learning, and we don't want that information to get elsewhere. We can use it also for authenticating media. So you can use machine learning to create images, to create videos. And pretty much now, they're so good at it, it's difficult to know whether something is real or not. There are some projects going on that use zero-knowledge proofs to show that if you have a certain image and you change that in a certain way, say you change the background, you can prove that that's all that has been done to it. So you can really specify what changes have been done to an image, and that makes it more authentic. Okay, I'll skip the next point because I won't go quickly. Has anybody used the orb from World? No? Okay. So you get, as a World ID, they're a company, they do come to a lot of Web3 events. They have this thing called the orb. What you do is it scans your retina and it gives you an identity, and it's a proof that identity is proof that identity is human, and it uses biometrics, it uses machine learning to do whatever, but it needs to have privacy as well. So they say that biometrics is not going to leak. So yeah, that's one of the use cases. This is fairly old, but this is from Los Alamos. It's about decommissioning weapons. I got this slide, they provided this slide. Just wants to point out that this is kind of zkML because they have a neural network. I think they have images that are being checked to show that the weapon is being decommissioned. And then they need to create proofs of that, but they don't want to give away information about what they're doing. So it's all done in zero knowledge, but it can be verified. This isn't my slide, so I don't know what Darth Vader is about on there. I'll skip this one. So one of the basic problems we have is that neural network, the diagram I showed you. How do you represent that in zero knowledge? How do you create a zero knowledge proof from that? We need to represent that in some way. And the major problem is the underlying mathematics, even though the actual sort of architecture of these things looks quite similar. The layers of the neurons, the way the neurons fit together in a machine learning model is quite similar to how zero knowledge proofs represent computation in what is called, they have arithmetic circuits which look very similar. But then this is problematic. Some people have managed to do this, so these are some of the projects in the area. So zkML is confusing because that's the general topic, but it's also a particular project. One of the main ones is zkML. If you're thinking about developing, that's one of the ones I would recommend using. They use a standard format. If you've done machine learning, you will know the Onyx format. This is a way that you can represent the architecture of your machine learning model in a standard way, so it can be used in different models. Risk zero, this is a way to prove any type of computation, but they also do it for machine learning. Mina, if you know the Mina blockchain, is on layer 1. They've also just released a zkML library. This is another one that is pretty good if you're a developer to start with. Soundcheck and GKR, these are zero-knowledge proof protocols that are also being used, but I'll skip over those. So with zkL, yeah, I've mentioned that, I'll skip that. What they do, though, to try to get around these problems is they have a number of techniques that they use. So they try to tweak the way that zero-knowledge proofs work so that they will work better with machine learning, and they can try to overcome some of the problems. So there's a couple of the approaches there. But I won't go through this. We can come back to them if you want to. One point they do, quantization. What this is, when you've got your machine learning model, you've got all of these weights in the neural network, trillions of weights potentially. And these can be very big numbers, but they can be decimal numbers. What you can do is reduce the number of decimal places. So you can kind of make these numbers smaller, and this is called quantization. It reduces the accuracy a little, but it can still work. So that's one possible way to help with the zero-knowledge side. The non-linearities, this is because of the transform, the activation functions that I showed you on an earlier slide. These behave in a kind of a non-linear way, so it's not a very predictable way, which is great for machine learning, because that's one of the things that helps a machine learning model to do the amazing things they do. But again, ZK really doesn't like nonlinear stuff, and so there are techniques to kind of try to get around that. This is what Mina does, kind of similar, but Mina is all about recursive zero-knowledge proofs, and that is one approach that I think is has quite a lot of potential, because you could recursively go through these layers of a neural network, creating partial proofs as you go along, and that could help with performance. I'll skip this one. So this, about a year ago, I was giving talks and giving courses and saying all of the problems we have with zkML, and it's just not performant enough. And then this thing happened, which was kind of seen as a breakthrough. So there was a large language model, ChatGPT-2, which has about 1 billion parameters. Okay, and Modulus Labs managed to create a zero-knowledge proof of this, and this was seen as something of a breakthrough because nobody had managed to do a proof of anything quite so big. To do that, though, the actual setup took 90 hours of processing. To actually create the proof took another 90 hours. So it was, not simple, but still they managed to do it. So that was seen as a breakthrough, and we are getting better. But of course, that was ChatGPT-2. GPT-4, etc., they're going to, orders of magnitude greater in terms of the number of parameters. Another project, zkLLM, so they're, particularly targeting large language models, which is the ones that, everybody's using. And things like zkReLU, this is the activation function. So they're writing very specific components to target the things that machine learning models do, and doing ZK versions of that. Other ways that you achieve this, though, off-chain computation, Mina does that very well. Recursion I've mentioned. One thing I'll come to in a second is weightless networks. I'll come to these next points, actually, I've got slides. So this was a project from a couple of years ago from a hackathon. He won a hackathon at Lisbon. What they did was to use neural networks which didn't have weights, which is a fundamentally different way of doing machine learning. They found that there was this, an old way of someone had proposed of doing machine learning that hadn't been thought of or hadn't been used so much. It didn't use weights and therefore was much more amenable to zero-knowledge proofs. Going the wrong way. This paper came out just recently, so last week it was presented at ZK Proof. So Nevermind Research brought out a zero-knowledge proof protocol. The important thing about this, which could be very interesting for machine learning is that instead of being restricted to integers, it can work with rational numbers, so it can work with fractions. So that sort of opens up a large area that could be very useful. Other things. If you don't want to use zkML, an area that does similar things that's been around for a long time is federated machine learning, and they have ways that people can combine data to train models, and it relies on certain aspects of cryptography, but not zero-knowledge proofs per se. So the problem with all of this is that doing zkML is costly in terms of time. You know, the 90 hours to set up, the 90 hours to create a proof, that's far too much. These are some benchmarks. So you can see risk zero. This is a kind of a general purpose proving system. And to create a proof, 10 seconds. This is a very simple machine learning model as well. It's linear regression. So we still are not getting these proofs as fast as we would like. But some other approaches are doing better. So zkLLM, because they are concentrating on a particular type of machine learning, are able to sort of tweak it and do things much quicker. But still, 15 minutes is not feasible. You want things that you can do on your phone in a second or so. Okay, I've got about a minute or so for questions. So yeah, let me ask me anything. Go, Dad. No.
How's development? Like, where do you think the developing?
Yeah. So you're asking how do you develop it?
So when will it become actually usable for people? Like, what's your expectation?
So you can use it, yeah. So zkL you can do now. So you can use Jupyter notebooks. You can import models. You put them in this ONNX format, the standard format. You can start with TensorFlow, something like that. Getting into the ONNX format, and then it will create a proof for you. So yeah, you can develop it. Right. So I'll have a look at zkL. That's probably the best one. Yep. Anyone else? All right, so I think we're finished then. Thank you very much for coming. I appreciate it. It's early in the morning. Thank you.